So let's talk about a few kind of important things, overall things. So yeah, first, no class on Wednesday. No labs this week because of Thanksgiving. This is our last week of no lab. This is our third one in a row. And then remember that school is closed Thursday and Friday. So I guess what I still haven't graded of yours is the weekly assignment that you turned in pretty recently. It might even be due today, but I can't remember. Maybe Friday or something. Last Wednesday. So I haven't done that. And I still haven't done a quiz, I think. But everything else is graded right now, including all the late stuff that took me a long time to get to. So if you emailed me any stuff, that all should be updated. So everybody, please check your grades on D2L and make sure everything is there that should be there. The percents should be basically what your standing grade is. The grade cutoffs are 90, 80, 70, 60. So you should be able to tell very clearly like what your grade is at right now. So please look at that and contact me if you have questions about it. It's important that you do it now because for anybody who's thinking about possibly withdrawing, the deadline is on Wednesday. Okay, so I mean that doesn't, not too many people are affected by that, but if you're thinking about it, the withdraw deadline is Wednesday. Okay, and so if you're thinking about possibly withdrawing, it is my strong advice that you should make an appointment with an advisor before you do, because there could be financial aid implications of it. So you just want to make sure that you don't have any kind of surprise about that. So anyways, yeah, this is a good week to just sort of take inventory of where your grade is. I know there are a lot of people who still are missing a lot of assignments. I don't really like to, look at a million assignments just all dumped at the last minute. But if you have assignments and you are still planning to get them in that are, already past due, contact me and let's talk about it, okay? All right, anybody have any questions about grades and stuff like that? Okay. Since we're about to have a week off from this class, I thought I would just spend the day putting problems up and letting you work together, work through problems, kind of like a review, catch up with where we are. So let's do some of that.
I do have a question.
Yes.
Actually, it says like next week, I think we have, maybe it's the week, a lab exam, and I'm just wondering if what the content's gonna be, since we haven't had a lab and since like.
Yeah, well, all the quizzes and exams it's always cumulative.
Okay.
So, yeah, we're going to have, next week we're going to have one new thing, one new topic, but then, I mean, it's still just trying to make sense out of the stuff we've been doing all semester.
Sounds good, thank you.
Okay. Okay, so let's say that we have a horizontal surface and two carts that are connected by a cable. Let's say this one is 15 kilograms and this one is 40 kilograms. And let's say that there's 150 Newton force applied this way and a 30 Newton force applied this way. Let's put a 25 Newton force down like that. Okay. So first, let's calculate the acceleration vector of the system. Second, let's calculate the force that's applied. So this is a force vector, bless you. Calculate the force vector applied to the 15 kilogram cart by the cable. And then third, calculate the force vector applied to the 15 by the ground. And so we're just going to do this piece by piece. I'll just take time for you to work on each separate step. So first, just do part A. Calculate the acceleration vector. Make sure that you draw a free body diagram before you use Newton's second law. You have to always do that before Newton's second law. And feel free to talk to each other, compare answers as you go, ask me questions if you're stuck. And after I give you a little time to do it, I'll go through it. So for the first part, to calculate the acceleration, this is a problem where everything has the same acceleration. And you can tell that everything has the same acceleration because there's no pulleys. And so we're going to start by isolating the entire system together. So our free body diagram is like this. We have one cart. And then the second one. And then we have the forces. So 30 newtons this way, 150 this way, 25 down. Those are all the given forces. And then there's the weight force. This thing has a mass of 55 kilograms. So the weight is 55 times 9.81. So that's 539.55 newtons. And then there's a pushing force from the ground. I'll call this N total. And now that we have all the force vectors, we can go to Newton's second law. The 30 Newton force, that's in the negative x direction. So this is negative 30, 0. The 25 is in the negative y direction, so 0, negative 25. The weight is 0, negative 539.55. The normal force, that's in the positive y, so 0, N total. And the 150 is in the positive x, so this is 150, 0. And all these add up to equal the total mass, 55 kilograms, times the acceleration. Is this system free to move along the x or y axis? X, so this acceleration is going to be a0. Okay, well, we're trying to calculate the acceleration, and so the acceleration is a0. That means that all we need to solve for to know the acceleration vector is this variable a. So all I need is the x equation. So the x equation says negative 30 plus 150 is equal to 55a. And so a is equal to positive 2.18 meters per second squared. Now we want the acceleration vector, not just this variable. So remember that whatever I ask you for, almost always, is going to be something that's already appearing in Newton's second law. This is the acceleration vector we already came up with. We just didn't know what a was yet, and now we do. So plug that in, and you get that the acceleration vector is 2.180. Any questions about that? Okay, so the next part is, B and C both, we're trying to calculate some force vectors that are acting on the 15 kilogram cart. So now that we know the acceleration, now we can isolate a single cart. The 15 is the one that we want to do. And so for part B, isolate that 15 kilogram cart and see if you can calculate. You might as well do the two of them together. Let's do both B and C. I'll give you a little time to work on it, and then I'll do it again. So now that we have the acceleration, we're going to isolate the 15 kilogram cart. And acting on the 15 kilogram cart, there's the 30 and the 25. So 30 newtons this way, 25 down. The 150 is not acting on it. That's acting on something else. So that doesn't go in there. There's a weight force of 15 times 9.81, so 147.15. There's a pushing force from the ground, so I'll call that N15. And then there's a pulling force from the cable, and I'll call that T. So there's the complete free body diagram. And then Newton's second law says negative 30, 0, plus 0, negative 25, plus 0, negative 147.15, plus 0, N15, plus T0, is equal to the mass, 15, times the acceleration vector that we figured out in part A. So 15 times 2.180. Okay, the vectors that we're trying to calculate are the force applied to the 15 by the cable. So that's this one. And the force applied to the 15 kilogram cart by the ground. So that's this one. Well, you can see they show up in different equations, so we're going to have to use both of those two equations. The x equation says negative 30 plus t is equal to 15 times 2.18. So 32.727 And so t is equal to 62.73. I'll round it there. Okay, but this isn't the vector. The vector is when you take that answer and put it back into, in this case, the red vector that's circled above. So the force on the 15 by the cable is 62.730. Or you could write it in the positive x direction with a magnitude of 62.73. And then we also want this green vector. So for that, I'll use the y equation. The y equation says negative 25 minus 147.15 plus n15 is equal to 15 times 0, so 0. And so n15 is equal to 172.15 newtons. Now plug it into the green vector and you get that the force on the 15 by the ground is equal to 0, 172.15. Or if you want to visualize the direction, that's in the positive y direction with a magnitude of 172.15. Yep.
Because I know like technically, wait, never mind, I take it back. I was like, isn't it a negative? But then we add it to the other side.
Right, you add to the other side, exactly. Any other questions? Okay. So here's another one. So let's say this time we have a ramp that makes an angle of 30 degrees with the horizontal. And there's a block on the ramp. Let's say the block has a mass of 3 kilograms. And it uses the pulley to connect to a hanging mass of 2 kilograms. And let's say the coefficient of friction between the 3 kilogram block and the incline is 0.1. And let's say that at this instant, the block is moving this way, which means the hanging mass is moving this way. So first, let's calculate the acceleration vector. And let's do the acceleration vector of the hanging mass. And then second, we'll figure out whether it's speeding up or slowing down. And I guess we might as well do this all in one step. The second one is kind of immediate after you get the answer. So see if you can work your way through this problem. And again, show answers to each other, show answers to me, whatever. This is just your time to try to make sure this stuff is solid in your head. So this one, the acceleration of these two bodies is different. And you know that because there's a pulley in there. And so that means we have to treat it a little bit differently. We're going to choose one of those bodies to isolate, start with that, and then go to the other body. Okay? I think most people probably chose the 3 kilogram as their first body. Is that right? You can do either one. The answer in the end will come out the same. So let's do a free body diagram of the 3. And it looks like this. There's a weight force down of 3 times 9.81. So that's 29.43. There's a pushing force from the ramp. I'll call that N. And then the only other force is the friction force between the ramp and the block. We can see that the block at this instant, its velocity is up the ramp. So the friction force is down the ramp, opposite that. And it's equal to the coefficient times that pushing normal force. And usually the only thing that we have to figure out using cosine and sine are the components of the weight force, because when we look at this one, we're using a coordinate system like this. Okay, so here's our coordinate system.
Is there a reason why there's not tension as a part of the free body diagram?
Oh my goodness, thank you. I forgot to put it in there. Yeah, there has to be tension. I guess I'm just so used to doing these where it's just, sliding.
Yeah, no, that makes sense.
Okay, so here's the coordinate system. And then the weight force is straight down. And you always know, and so the magnitude of this is 29.43. You always know that the angle that the ramp makes with the horizontal is the angle the weight force is going to make with 270 degrees, the negative y-axis. So we know that this angle is going to be 30. Okay, so if you go counterclockwise from the x-axis, what's the angle to get to the weight force? 240. Yep, you don't make it to the negative y-axis. You're 30 degrees short of that. And so theta is equal to 240. And so that weight force vector is 29.43 times the cosine of 240. 29.43 times the sine of 240. And you get negative 14.715 for x, negative 25.49 for y. So now we can go to Newton's second law. And just one by one, we're going to go through these forces. The first one I'll put in is the weight force. That's the one we just calculated. So that's negative 14.715, negative 25.49. Then I'll do the normal force. That's in the positive y direction of our rotated coordinate system, so plus 0n. The 0.1n is in the negative x direction, so this is plus negative 0.1n, 0. The only thing left is that cable force. That's in the positive x direction, so T0. And all that's equal to the mass, 3, times the acceleration. This is the first body, so all we have to do is decide whether it's moving along the x-axis or the y-axis. Which one is it? X. And so I'll write this as A0. We don't have to think about the signs yet. And the x equation says, well, actually, since we have friction here, let me just do the y equation first. So we have negative 25.49 plus n is equal to 0. Solve for n and you get 25.49. And then we'll plug that into the x equation. So the x equation says negative 14.715 minus 0.1 times n, but we just calculated n, so I'll put that in here for the normal force, 25.49. Plus t is equal to 3a. And I'll simplify this a little bit. So we get negative 17.264 is equal to 3a. No, I left off the t again. Negative 17.264 plus t is equal to 3a. Okay, so this is our first equation that we're going to use in our system to solve for a and t. But we can't go any farther with it because we have one equation with 2 variables, or if you include the other one, 2 equations for 3 variables. Either way, you can't solve for everything. So now I'm going to do the hanging mass. That one is 2 kilograms. And for this one, I'm not going to use this crooked coordinate system anymore. I'm going to use just a regular coordinate system for talking about this one. Yes?
So like throughout like all of our systems, as long as it has different accelerations, we can use different coordinate systems?
Yes. So it makes sense, I think, if you think about it like this. Like when we're coming up with systems of equations, all we're trying to do is come up with multiple equations that are true, you know? And another important thing is the variables have to mean the same thing, you know? But as long as we, everything we say about the block is true and everything we say about the hanging mass is true, which coordinate system you're in doesn't matter. Okay, so the weight force is 2 times 9.81, so 19.62 down. And then there's a pulling force from the cable. It's the same cable as before, so it's still called T. And then Newton's second law says 0T plus 0, negative 19.62 is equal to the mass times the acceleration. And this is the trickiest part of these problems where the accelerations are different. Now is when you have to think, okay, I'm going to go back to this first body and imagine it moving an inch in its positive direction and figure out where the second one goes. Okay, so the 3 kilogram, if it goes an inch in its positive direction, that's up the ramp. Okay, that means that that 2 kilogram mass would go an inch down. Okay, that's the negative y direction. And so our acceleration expression for this second one needs to be in the negative y direction. So I'm going to write this acceleration as 0, negative a. And then the y equation here says negative 16.264 plus t is equal to 3. No, I'm looking at the wrong one. It says t minus 19.62 is equal to negative 2a. And now it's just a matter of solving those two boxed equations. Okay, so now the physics is done, it's just the math really. But from this one, I can rearrange it to say t is equal to 3a plus 17.26. I'll round it to that. And now that I have an expression for t, I can plug that into for t in the second one. So the second equation now says 3a plus 17.26 minus 19.62 is equal to negative 2a. Add 2a to both sides, and you get 5a is equal to 2.36. And so a is equal to 0.47 meters per second squared. Now, whichever one of the accelerations you want, whichever body you want the acceleration for, you just have to plug that a into the correct acceleration. I asked for the acceleration for the hanging mass. That's this. So now I just have to plug positive 0.47 in there. So the acceleration vector of the two is equal to 0, negative 0.47. Or in other words, it's in the negative y direction. Any questions about that? Okay, let's do an energy one. So let's say there's this loop-de-loop, and this skateboarder wants to do this sick trick. So rad. I don't know if I've ever tried to draw a skateboarder upside down before. Okay, so the skateboarder wants to make this loop-de-loop. Yes?
I was just wondering about the last problem. How are we able to know if it slows down or speeds up?
Oh, yeah. The arrows indicating the direction of motion are telling you the velocity. So if the acceleration is in the same direction as the velocity, it's speeding up. If the velocity and acceleration are in opposite directions, it's slowing down.
We need we need to know the velocity.
You need to, for these problems, you need to know it anyways, because you can't tell the direction of the friction force until you know the direction of the velocity. Yeah. Okay, so let's say the radius of this loop-de-loop is, what's a good, let's say it's 2 meters. 1.5 meters. No, that's too little. Yeah, let's say 2 meter radius. I think the answer might be he has to go really, really fast, but we'll find out. And what we want to figure out is how fast does this skateboarder need to go at the bottom to complete the loop. Okay, so here's the way we're going to go about this problem. We're going to do it in reverse. We're first going to figure out how fast the skateboard has to be moving to make it over the top and stay in circular motion. Once we figure out that speed, the minimum speed that the skateboard can go and still stay in circular motion, then we'll use conservation of energy to figure out the speed at the bottom. Okay? All right, so first, what's the slowest the skateboarder can go at the top to stay on the loop? So the first thing you have to do is figure out an expression for the, so find an expression for the acceleration at the top of the circle using the speed v. Okay, so go through the steps of circular motion and see if you can come up with an expression for the acceleration in terms of that speed v. Okay, this is not a tetherball problem, so go through the steps where you're looking at the path. So the path that we're looking at is like this, and the point that we want is up here. The velocity is this way. The centripetal acceleration is this way. And at the top of this circle, since the height isn't changing, the speed isn't going to be changing. So all we need, the total acceleration, is just going to be this centripetal acceleration. The magnitude of the centripetal acceleration is the speed squared over r, which was 2 meters. And so now our centripetal acceleration vector, which is our total acceleration, is 0, negative v squared over 2. Now, the next step is draw a free body diagram of the skater at the top, and we're going to use Newton's second law to calculate the smallest value that v can have. So now use Newton's second law to find the smallest possible v. Do you remember what we do with the normal force in problems like this? We've done 1 or 2 of these. Well, what we're going to say is the limit of this person being able to maintain that loop is if we're going to say that the person stays in that circular path, it's when the normal force crosses over from being a pushing force to a pulling force. The ground can't pull. And so that normal force, we're going to set the normal force equal to 0. So see if you can go through, draw the free body diagram, and use Newton's second law to calculate what V is. Anybody want more time for this? Okay, so a free body diagram at the top of the circle looks like this. So here's the skateboard. Here's the skater. Upside down. There's a weight force down. So I'll call that 9.81 times the mass. I didn't specify the mass. And there's a normal force pushing down from above. There are no other forces, so Newton's second law says 0, negative n, plus 0, negative 9.81 m is equal to the mass times the acceleration that we got in the first step, 0, negative v squared over 2. And like I said, the cutoff is when this is equal to 0. So now our y equation says negative 9.81 m is equal to negative m v squared over 2. And now you see you can divide both sides by negative m. Get rid of the negatives, get rid of the m's. V squared is equal to 19.62. And so V is equal to, we want the positive because it's a speed, 4.43 meters per second. Okay, that's the slowest this person can be at the top. Now we want to figure out if the person is that fast at the top, use conservation of mechanical energy to calculate the speed at the bottom. Okay, so see if you can, conservation of mechanical energy. I'm going to call instant 1 at the bottom of the circle and instant 2 at the top of the circle. And I'll call height equals 0 the bottom of the circle. So let me draw that picture. So this is what I'm going to call my h equals 0. So then at the bottom, the gravitational potential energy is the mass times 9.81 times the height of 0. And we're trying to calculate the speed, so the kinetic energy is 1/2 times the mass times the speed, v squared. We're trying to calculate that v. At the top of the circle, the gravitational potential energy is m times 9.81 times, if the radius is 2, then the diameter all the way from the bottom to the top is 4. So this is 39.24 m. And the kinetic energy is 1/2 times the mass times the speed at the top squared. So now we're going to put in that minimum speed to stay on the path. And that is 9.81 m. And now finally just put this into conservation of mechanical energy. 1/2 mv squared is equal to 39.24 m plus 9.81 m divide both sides by m. And you get that v squared is equal to 98.1. And so the speed is square root of 98.1, 9.90 meters per second. So if this person can be 9.90 meters per second at the bottom, they'll get up to the top and make it over. Okay, that's all. So there's no lab, but I am going to be in there. If anyone has questions, I could talk about grades or assignments or things that are confusing you on homework or whatever. And then otherwise, have a good Thanksgiving, and I'll see you Monday.